Right, the next topic that we're going to be doing is structure, bonding, and thermochemistry. What I'm going to give you now is a bit of an overview about structure and bonding, in particular to do with the bonding between the particles in solids. So whenever we're thinking about these substances, think of them in their solid state. Even if we're talking about carbon dioxide, for example, which is normally a gas, think of it as dry ice. Even if we're talking about water, think of it as ice. Alright, so everything we're looking at is based around the side of solids. Then we can look at what its melting point is, what its boiling point is, whether it sublimes or not, whether it conducts electricity. We can look at those physical properties of that solid to help explain the bonding between the particles. The reason we focus on solids is this is where the bonding is at its strongest for any of these substances. So for example, for wax, that when it's a solid, that's when its bonding is at its strongest. Of course, a little bit of heat, it starts to melt, a little bit more heat, and it becomes a gas which can then burn. Alright, so that's why it's a fuel. So we're really looking at solids. And solids are one of the states of matter, or one of the phases of matter. So this topic is all about matter, how matter is organised. Now in year 9 and 10, and probably even last year in year 11, we probably split matter, so I'm going to say solids now, solids into two main types. Things like alloys, which are made up of more than one type of atom mixed together, and things like iron, where it's only made up of the one type of matter. So we've got pure substances and we've got mixtures. I'm going to put pure substances over here, mixtures over here, because mixtures we're not going to worry about. For us to analyse what a mixture is made up of, we first of all need to split it into pure substances and then analyse what those are. So this topic is not about mixtures. What we're going to focus on in this case is we're going to say, well, we've taken these mixtures and we've purified them. We've made them pure substances. So hopefully this looks relatively similar to some little key that you created in junior science or year 11 science. Right, our pure substances can be broken down again into another couple of major groups. If we have a look over on the right hand side of the room, then you can see a way of having certain things organised. What is that category of pure substance called?
Noble gases.
We have got the noble gases as an example of these, but they are all... There's some non-metals there as well. So we've got metals and non-metals, and noble gases are all examples of what? Have a look at the heading of that chart. Elements. So we've got elements. And as you said, they can exist as the noble gases, so those sorts of things. So we've got the... What are the noble gases? What do they exist as? Yeah. So why are they gases? The forces are very weak between the particles because they're stable.
They've got full outer shells.
They've got full outer shells, so they exist as atoms. Correct? Okay. So elements can exist as atoms. That's one example they could have, that we could have of these. And you've just said noble gases, which is great. Is there anything else on the periodic table that exists as atoms? Metals, good. Now that's not strictly true, okay? But we will put it under this classification because for level 2, they're happy for you to call them atoms. They're not really atoms, and I'll talk about that just for a moment now. So we've got the metals. Metals really are cations in a sea of electrons. Their valence electrons are not held that tightly. Valence means basically the outermost electrons. They're not held very tightly. So what happens is every atom actually contributes its valence electrons to a sea. So if I had, for example, iron, iron, I'm pretty sure it breaks into the iron 3 plus ions. Probably look that up and find that it's actually the iron 2 plus, but for all intents and purposes, let's say it breaks up into iron 3 plus ions. Then the 3 electrons that it's lost to become the ions all get put into a communal sea of electrons which can flow. Alright? What it does is it creates a relationship between these nuclei, that they are held in place by some bonding, but it's not so hard that you can't change the direction of the bond. It's able to allow it to be malleable. So I can move the position of these nuclei without actually breaking the metallic bond. But technically speaking, they're all just Fe, because their electrons haven't been lost anywhere, they're still part of the substance. So that description of them being atoms is still loosely correct. So we say that the examples of elements which exist as atoms are the noble gases and the metals. Okay, what about oxygen, nitrogen, chlorine, bromine, iodine? What do they exist as? They are non-metals. Good, they're examples of non-metals.
Gas.
They, not all gases. Bromine's a liquid, iodine's a solid, sulfur, which is S8, is a solid. They're not ions in this case. They're molecules. Good. Okay, so they're discrete molecules. They float around as O2, N2, S8. We say just C for carbon because that's what we call a macromolecule, okay, or a covalent network. So we have molecules. Okay, and some examples, I only give examples here. O2, N2, S8, they're probably some good ones. You've also got the macromolecules, which is sort of a subset of this. And here we're looking at graphite and diamond. Now the word we use for these is they are allotropes of carbon. They're different arrangements of the carbon atoms, which gives it different physical properties, but it's still an element, just made up of one type of atom, and it's still held together by covalent bonds. So we call these covalent networks, graphite and diamond, and they're pretty cool. Graphite's in sheets with a valence electron, a lot like metals actually. A valence electron contributed from each carbon atom in between each sheet, and that's why graphite is a lubricant. The two sheets can slide over each other. It's also why graphite's quite a good conductor. It's got a sea of electrons, it's got a charged particle that can move freely. Right. So there are elements here, atoms, okay, noble gases because they're stable, pull out a shell, and your metals. Elements can also exist as molecules. Okay, so we've got more than one atom of the same type joined together. Alright, well if things aren't elements, then what else could they be? The topic you often do in junior science is called elements and compounds. Great. So other major option is to have compounds. And this is where I reckon it gets really interesting, because this is about the relationship between different elements joining together. So atoms from different elements joining together. And here, again, you can have molecules. You can have discrete molecules like water, wax, those sorts of things there. And what sort of bond holds the atoms together in those sorts of things, whether non-metal and non-metal? Covalent, good. They have to share electrons to complete their outer valence shell. So we have covalent compounds, which are molecules. So I'm just trying to get the colours right here. Okay, so we've got the molecules. Again, I'll give some examples. Glucose, C6H12O6. Water, really good example. Carbon dioxide, or dry ice. Right? If we look at their physical properties, we can start working out a bit more about them, and there's going to be a heap of work on that. The key words to look at here are that we're going to be looking at the intramolecular bonding in these. And intra means inside, so inside the molecules. This means the covalent bonding between the atoms inside the molecule. So in other words, is the carbon bond what we call a pure covalent bond, or is it a polar covalent bond? Or is it nearly an ionic bond? Because sometimes there's a bit of a blurry region there. We're also going to look at the intermolecular bonding, or the forces, or sometimes called van der Waals forces, that exist between each molecule. So why is sugar a solid at room temperature? Why is carbon dioxide a gas at room temperature? That sort of thing. And that's determined by the intermolecular forces or bonding, which again I said are called van der Waals. This here relies on a couple of other key words. We look at polarity. So the polarity of molecules, the polarity of bonding, so intermolecular and intramolecular forces are determined by the polarity of the covalent bond. To determine that, we need to understand a thing called electronegativity. So that's going to be another really important idea that we're going to need to understand in this section. So this is a really big part. And the last thing, to understand all of this properly, the last thing you need to really know, and very importantly so, is about shapes of molecules. Because that determines whether the molecule is polar or not. For example, if I charge a ruler, put it next to a stream of water, the stream of water gets attracted to that charged rod or that charged ruler. That only happens because water is what we call a polar molecule. If I did the same thing with petrol, nothing would happen. Okay. Now the other type of compounds we could have, I sort of implied before in my description, I wonder if you caught up on it. If we don't have covalent bonding, we have ionic. So electrons are now transferred. Actually, I need the brackets there, sorry. So we have our ionic compounds as well. Now, these are things like your classic salt, NaCl, and other salts and crystals like magnesium chloride, but even more complicated ones like your potassium permanganate that you'll meet later. And sodium carbonate, which you met very recently. Okay, things like that, held together, while the carbon and the oxygen, by the way, and the carbonate ion are held together by covalent bonds. CO3 has a -2 charge, so it is held to the sodiums by an ionic force. So you can see you can start getting combinations within the one thing. Okay. To understand this is actually a lot easier. You're really just looking at, is it a metal with a non-metal or a metal with a group of non-metals usually. Again though, we have to understand electronegativity to really understand whether something's going to be ionic or not. Then ultimately, all of this, so all the pure substances stuff, you need to link to a couple of things. You have to link it to the melting point and boiling point of that substance. If it's got very, very high melting and boiling points, then the forces between the particles must be very, very strong. So it's probably going to be ionic, or it's going to be one of these macromolecules, because it's got lots of bonding. You need to be able to look at electrical conduction. Because only charged particles, whether that's electrons or ions, can carry a charge, because they are charged. So they're the only ones that can allow a current to flow. But to flow, those particles have to be able to move. So if those particles are held too tightly in place, they can't move, so it'll be an electrical insulator. We also look at heat conduction because it can be quite useful at times. I'll talk about that in more depth when we actually do that. So what I call thermal conduction. Thermal is just heat. Alright. And the last thing that we have to look at is solubility. How well these things dissolve in different solvents. In particular, polar solvents versus non-polar solvents. So water versus something like cyclohexane or something like that. So solubility. To go with that, we also look at things like hardness. Are they very hard solids, so very brittle, or are they quite flexible? Are they malleable or not? Are they ductile or not? And those sorts of things. So we look at those typical things that you looked at last year when we studied metals. We still apply them to these. There's one thing I forgot. I'm sorry. There's one thing I've forgotten here. To understand shapes, you need to understand a thing called Lewis diagrams, which I didn't do, so I'm sorry. So to understand that, the other piece of knowledge you'll need to get is about Lewis dot diagrams. But in a nutshell, that's the structure and bonding part of this topic. I'm not going to go into the thermochemistry stuff here yet. I will leave that till we get closer to doing that part of the topic. But that, in a nutshell, is what we're going to learn in the next few school weeks.